When we consider atomic absorption and that we might want to use Beer's law with that, then we need to consider that Beer's law says that we must be using monochromatic light, especially for quantitation. And so when we're looking at using a range of wavelengths coming from a radiation source, we want that range of wavelengths to be much smaller than that of the absorbing sample. For instance, in the UV invisible range, we might have narrowed it down to a single nanometer of width of our coming out of our monochromator. And that was sufficient because the absorption band of the molecule was 20 or 30 or 100 nanometers wide. However, with atomic absorption, these bandwidths are so very sharp. We're looking at 10 to the negative fourth nanometers, and our monochromators are simply not precise enough for that. The limit to a grating monochromator is about 10 to the negative third or 10 to the negative second nanometers. So we're 1 or 2 orders of magnitude away from the precision that we need to have in wavelength selection in order to be considered monochromatic light for atomic absorption. So we're going to need some other kind of light source that's going to give us very monochromatic light. And the light source that we're going to talk about that fits that description is the hollow cathode lamp. Okay, so here's what a hollow cathode lamp looks like. Okay, we've got a hollow center here, and this is all sealed, okay, and I'm just going to draw this like this. Okay, so it looks kind of like a bottle on its side. Okay, what we have in here is we have in this bottle a quartz window. Okay, and we've talked about using quartz in other pieces of instrumentation because it allows more wavelengths of light through. It doesn't really absorb in the UV or visible regions. It has a very broad transmission spectrum. So we tend to like quartz for our windows here. Okay, now this whole thing is sealed and it's filled with argon or neon. And when I say filled, I use that term pretty lightly. Okay, we're only looking at between 1 and 5 torr, which, to put that in perspective, 1 atmosphere, which is kind of our normal pressure of daily living, is 760 torr. So this is pretty much under a vacuum, but whatever is there is not air, it's argon or neon. All right, now what else are we going to put into this? Well, it's named a hollow cathode lamp, and we are going to put a hollow cathode. This is going to be a ring cathode. So I'm going to draw this as a ring here. It's got kind of a hollowness to it. Okay, this is our hollow cathode. Okay, so we have a negative potential applied to the cathode. Now this hollow cathode is made of whatever element we want to be analyzing, and I'll get to why that is in just a minute. Negative element to be not the sample itself, but just the same element. So if you're going to do a calcium analysis, you would want your hollow cathode to be made of calcium. If you're doing an aluminum, you're going to make it out of aluminum. You're doing titanium, you're going to make it out of titanium. Okay, so that's our hollow cathode. But anytime you have a cathode, we know that we can't have just half of a circuit. We need to have a positive end, and so we're going to have an anode. And this is going to be a ring anode. Okay. All right, and we have connected these with some kind of a circuit to get our applied voltage. All right, so here we go. We have a hollow cathode made of our element. We have a ring anode. And then we're going to have kind of a disc in here that's basically going to separate our extra space from everything else. We've got this kind of disc that's in here. Okay, so what goes on in this hollow cathode lamp? So we have the ability to apply a voltage, and that's not there for any mundane reason, but we're going to actually apply the voltage, and what happens is we're going to ionize the gas, much like we did to make a plasma with the argon in the ICP, except here we don't have the density of argon to make a full-on plasma. But we will ionize the argon or neon that we've placed in the hollow cathode lamp, at which point we now have cations and ani, or cations and free electrons. So our ionized gas is actually going to go towards the cathode, and when those cations are going to strike the cathode, what happens is we're going to sputter some of the metal atoms from the surface. So whatever element was made, or whatever element the hollow cathode is composed of, is what's going to be sputtered off the surface by our ionized gas. Why does this matter? Okay, once these are sputtered off the surface, now we have gas phase metal atoms that are going to collide with the free electrons. Now those gas phase electrons are excited. They've been accelerated between the cathode and the anode, and they have a lot of energy. And just like we would do with exciting anything in the gas phase in the flame or in the plasma with the free electrons and those collisions, we do basically the same thing here. The high energy electrons collide with our gas phase elements that have been sputtered off of the cathode, and now we have excited we have our excited atoms. Okay, so whatever element we have in the lamp, if we were to look at the Jablonski diagram, they go from the ground state to an excited state with by collision energy. Excited by collisional energy. Okay. Once you have atoms excited, what can happen? Okay, they're excited by collisional energy, and then they can relax. And when they relax, they can give off a photon. Okay, so we have them being excited by collisional energy and then relax for emission of a photon. Now, Dr. Tran, you might say, why do I care about these photons that are being emitted by the lamp? Well, because these transitions are so specific, and we've talked about how these don't have much difference in wavelength. These are very tight, very, very narrow absorbing bands. Well, then their emission bands are equally narrow. And so what we've essentially done is we've taken the element of interest and made a photon lamp exactly of the wavelength that we need it to be for this element and this element alone. Now we have this photon that is element specific to the element of interest exiting the lamp here through the quartz window, and we'll send that towards our sample. Now the sample might be in a flame, it might be in a plasma, or it might be using a graphite furnace, whatever atomization technique we might have been interested in. But what this does is it means that our light source is incredibly monochromatic, which means we can use Beer's law for quantification of our element, because this wavelength is exactly the wavelength needed for absorption by our element in our sample. So our sample can do the same transition with the absorption of light. And so with the hollow cathode lamp, we actually can achieve our desired narrow bandwidth for light and also make it very specific for our element of interest. Now, if you want to analyze more than one element at a time, you're going to have to use multiple lamps, which can make it difficult just from an experimental design position. You typically can't get more than 2 or 3 analyses at any given time with these hollowed cathode lamps, and you would have to change out the lamp each time you want to change which elements you're analyzing. So advantage, you get the narrow bandwidth that you need, but a disadvantage, these are incredibly element specific, and there is no kind of universal hollow cathode lamp for for doing multi-element analysis.